Welcome to this explainer. Okay, today we are exploring a truly phenomenal piece of research that honestly feels like it's pulled straight out of a science fiction novel, but I promise you it is very much reality. We're looking at a 2026 paper published by João S. Ferreira, Spencer S. Topol, Pierre Fromholtz, and James R. Wooten. And what this team has done is basically bridge two incredibly complex worlds, the mind-bending reality of quantum physics and the visual artistry of computer graphics. They've proposed a completely new way to calculate how light interacts with materials on our digital screens, and it is absolutely brilliant.
Okay, let's dive into this. When we think about how digital worlds are created, we usually imagine light acting well, very predictably. A virtual sun casts a ray of virtual light, it hits a virtual rock, and it bounces off straight into the virtual camera. Pretty straightforward, right? But this brings us to the exact problem this paper tackles. What happens when materials actually fight back against light? Like, what happens when the material itself physically changes because the light hit it? That is a level of dynamic interaction that standard computer rendering has historically really struggled to deal with.
So, to truly appreciate the breakthrough here, we've got to first understand what we can call the limits of light in our current technology.
Take a look at the comparison here. Traditional rendering techniques, the ones powering the visual effects in massive blockbuster movies and your favorite high-end video games, they suffer from a fundamental structural limitation. They basically assume optical properties are entirely static. But dynamic reality, it's completely different. In the real world, especially when you zoom into microscopic scales, materials evolve dynamically in response to incident illumination. The very act of light hitting the material actually changes how that material behaves. And traditional rendering, it simply breaks down in these dynamic cases.
So, how do we fix this gap? Well, Ferreira and his team introduced an absolutely radical solution, a quantum shading framework. Let's look at how they totally threw out the old assumptions. So, the crucial point is their quantum collision model. This is the central breakthrough of the entire paper. The researchers have combined classical ray tracing, which is that traditional method of drawing lines from a light source to a camera, with literal quantum mechanics. By doing this, they can finally explore the effect of coherent light-matter interactions in rendering. They aren't just bouncing geometry around anymore. They are calculating the true, fundamental quantum relationship between light and matter. Now, you might be wondering how this actually operates, mathematically speaking, beneath the surface. When light enters a translucent object, think of marble or wax or even human skin. It scatters all around inside before exiting. It is notoriously difficult to render accurately. But now this team is modeling this subsurface scattering using strict quantum rules. We can break their framework down into 3 logical steps, and this brilliantly illustrates how the complex dance between light and matter is resolved. Step 1 is treating both light and matter as quantized modes. Step 2 is taking that subsurface scattering we just talked about and modeling it as unitary collisions. And finally, step 3 is making all of this computationally possible by pre-computing it using quantum computers. Let's take a closer look at what these steps actually mean for the rendering pipeline.
Let's unpack that first step. What in the world are quantized modes? Well, instead of treating a light beam as a continuous wave or just a simple geometric ray, the researchers treat the incident light and the material's own excitations as discrete, interacting quantum states. Basically, they're breaking down both the light and the material into their fundamental quantized components. This ensures that when the light hits the material, the simulation fully understands that both entities have the capacity to react and change on a quantum level. Then, in step 2, they define the scattering as a sequence of symmetry-constrained unitary collisions. Okay, I know that is a wildly dense physics term, but think of it this way. In classical rendering, light is often treated like a tennis ball just bouncing off a static brick wall. In this quantum model, the interaction is a highly reactive mathematical dance. The light and the material undergo complex unitary collisions that respect the deep symmetries of physics. Actually, scratch the brick wall idea. The wall isn't static anymore. It's literally dancing with the tennis ball.
But why go through all this incredibly complex math? Well, the ultimate payoff is physics-inspired materials. We are finally moving beyond cheap approximations to unlock chaotic, dynamic visual effects that were previously just impossible to simulate accurately.
Now, what's really interesting about this slide is the specific list of complex optical effects this model can finally handle. First up, non-integrable dynamics, meaning systems that are so complex they just don't have simple, predictable shortcuts. Second, chaotic optical responses, where the material scatters light in beautifully unpredictable ways purely because the material itself is changing. And third, multi-layer interference effects, capturing exactly what happens when light bounces between microscopic layers within the material. I mean, these are basically the holy grails of realistic rendering.
Now you might be thinking to yourself, okay, this sounds like it would take a supercomputer 1,000 years to render a single frame. But the researchers solved this practically. We don't need magic to render this. They demonstrate that these incredibly complex collision operators can actually be pre-computed using near-term quantum computers. By doing the heavy lifting beforehand, they generate standard BSDFs, that's bidirectional scattering distribution functions. Essentially, this means the quantum data can be packaged into a standard format that existing rendering engines can already read and use without exploding.
The real-world application here is just immense. I want to read this direct quote from the source's abstract, noting that this framework is enabling the rendering of new physics-inspired materials with distinct optical signatures. For video game developers, visual effects artists, and industrial designers, this is an absolute game-changer. It means creating digital materials that look and react to light with a level of authenticity and distinctiveness that we have quite literally never seen before on a screen.
So this brings us to a really fascinating frontier. By stepping away from the static illusions of the past and fully embracing the dynamic, chaotic reality of quantum collision models, Ferreira and his team have cracked open a massive new door for computer graphics. And it leaves us with one final, pretty wild question. Are we ready for digital worlds bound by true quantum physics? The tools are being built right now, and the visual future is looking incredibly dynamic. Thank you so much for joining me for this explainer, and definitely keep your eyes open for how these physics-inspired materials will reshape the digital media we interact with every single day.